In wireless channels such as Wi-Fi and LTE, the antenna strength is related to the spread of noise. If antenna strength is low, the spread is wider, and if antenna strength is high, then noise spread is very narrow, become narrow. Here, this area is transmitting 0 and receiving 0, and this area represent to transmitting 1 and receiving 1. But this area is, even though you transmit 1, but the receiver think it is 0, and this is transmitting 0 and receiving 1. So this part is error part, and if the bit error rate is proportional to area of this region. In noise distribution, the noise distribution is narrow for the wired channel. So if the noise distribution is narrow, then there is not much overlap region, so bit error rate becomes lower. And the most wired channel is in this case. In Shannon's paper, this phenomenon is quantitatively analyzed. The channel model is shown like in this figure. The transmitted signal is called XT, and then noise is added, and as a result, YT, received signal is XT plus NT. This is addition operation. And then probability distribution of XT signal is 4 impulse. The height is 1/4, so 1/4. Because in binary data, normally all of these 2, 0, 0, 1, 0, 1, 1, 1, 1, 0 has the same probability. So we assign -5 to 0, 0 case, and -2 volt 0, 1, and +2 volt 1, 1, and 1, 0 for 5 volt. So if you receive -5 volt, then you can say they send 0, 0. But if noise is added here, then in the received signal YT, the distribution will be spread like this. Assuming the standard deviation of sigma, standard deviation sigma is like this, and the power of received signal is original power plus square of sigma. So if you divide this range is dynamic range of received signal divided by sigma square, then you can calculate the number of signal which can be differentiated by using this channel. So in this case, if you use four level of signal, then you can decode it without much bit error rate. In the previous page, we used 4 levels in the one-dimensional axis, but we can make a signal in 2-dimensional. So suppose we have we make transmitting signal xt like this: a cosine omega 0 t plus b sine omega 0 t. Then by using a and b, we can send the 2-bit value. So in this case, a is this horizontal axis and b is vertical axis, and then we can make a signal, this signal, and like this, 4 signals. And then probability of 4 signal is 1 over 4, mean a quarter. Then if it transmitted and if we add noise, then the signal may be distributed like this. In that case, if a signal appears in first quadrant, it is recognized as sending 0 and 0. And if the signal appears in the second quadrant, it is recognized as 1, 0, and so on. So when noise is widely distributed, it goes beyond its own quadrant and then is perceived differently from the information sent. That is error. So in this case, we use this signal symbols in 2 dimensions. So previously, signals distributed one-dimensional axis or signals distributed in two-dimensional axis were investigated. In 2D space, cosine omega 0t and sine omega 0t was basis signal, and you can increase the dimension by increasing number of basis signal. Generally speaking, we can consider signal distribution on n-dimensional space. For example, if you think 3D, the transmitted signal resides in a sphere whose radius is square root of p, and the number of transmitted signal exists as points within a sphere. Binary data is designated according to the position of each signal point in 3-dimensional space. As a receiving side, if noise is added, the radius of entire sphere increase by sigma square, so noise strength, and each small point becomes a tiny sphere whose radius is standard deviation of noise. So how many different signals are possible inside of the sphere? So it is how many tiny sphere can be put in large sphere. Roughly, the volume of big space is divided by volume of tiny sphere. Then we can calculate the number. Log 2 of the number represent how many bits at one time. So how many times a signal can be changed per second is related to how large the analog bandwidth in hertz. So transmission channels analog bandwidth. The number of times can be changed per second is directly proportional to the analog bandwidth in hertz. Finally, the equation became like this. Here, P is power of the signal, and N0W is the power of noise, which is square of standard deviation sigma. P over N0W becomes SNR, signal to noise ratio of the channel, and the maximum bit rate can be calculated by using this equation. The unit of analog bandwidth W is Hertz, and the unit of this channel capacity is bits per second, but both are inverse of second. So that is, the unit of C and W are the same. This graph is graphical representation of Shannon's equation. Basically, when SNL increase, this is SNL increase, the channel capacity also increase. In most countries, analog TV channel are converted to deliver digital TV right now. There are three kinds of TV channel: terrestrial channel, satellite channel, and cable TV channel, through which TV signal is transmitted. All were analog bandwidth 5 MHz channels. In the days of analog TV, no matter which channel you use, you could only watch one TV program through one channel. But the terrestrial channel had the worst quality, and the cable TV channel had the best quality. This is because cable TV has the highest SNR, signal to noise ratio. However, when switching to digital TV, the difference in SNR does not appear as a difference in image quality, but as a difference in transmission speed. That is, in Shannon equation, W is all the same 5 megahertz, but because the SNR is different, channel capacity C become different. Terrestrial channel can transmit 20 megabps through a 5 megahertz channel, and satellite channel can transmit 30 megabps, and the cable TV channel can transmit 80 megabps, respectively. For this reason, in cable TV, multiple sub-channels are possible in one channel. How can it increase channel capacity C? First, you can think of increasing the analog bandwidth W. However, in most cases, analog bandwidth W is fixed. You can see in this picture here, the use of air waves has already been decided. This is reserved for radio broadcast, and this is reserved for TV broadcast. In this way, the use of analog bandwidth is determined by law, and the broadcasters at the telecommunication companies pay large amount of money for the band they want, and use the right to use it in each country. In the case of transmission over a wired communication line, the analog bandwidth W is determined according to the physical condition of communication line. Therefore, it is not possible to change W in most cases. So how about increasing signal power, S or P, in Shannon equation? Increasing signal power can be implemented by increasing the transmission power in communication devices. In the case of a cell phone, that means battery runs out quickly. Think about radiological medical imaging system like CT. In this case, increasing the signal power means getting more radiation. So after all, in most communication studies, increasing channel capacity is according to increasing SNR, signal to noise ratio. One way to increase SNR is to use multiple antennas. Number of transmission antenna may be multiple, or number of receiving antenna may be multiple. MIMO, here MIMO, represent multiple input, multiple output. The purpose of several multiple antennas are attached to your Wi-Fi repeater is to increase SNR. In 5G, various methods are used to increase channel capacity, but the most important thing is to narrow the distance between the base station and the user. The signal strength decrease in inverse proportional to square of the distance between the base station and the user. Therefore, the closer distance is, the greater the strength of the signal. This is why base station need to be built more densely as the transmission from 4G to 5G. So this red point means base station location, and this is a cell in 4G, and this is a cell for 5G. So in 5G, cell size becomes much smaller than the case in 4G. So that is the most important way to increase SNR. Up to now, we learned about very important equations in communication and the information theory. So information amount and the entropy and the Shannon channel capacity. These equations are very important to understand digital communication, also digital signal processing. Okay, thank you.